it's my pleasure to talk about my recent research here. The title is Being an Only Child Harmful to Psychological Health? And from the subtitle, you can see it's a data analysis based on China's one-child policy. Evidence from an instrumental variable analysis of China's one-child policy. This is a joint work with Shu Xizhen and Fan Li from Duke Statistics. When we started, Shu Xizhen was a visiting undergraduate student. Now he's a fourth year PhD student now. So it has been several years. And this paper will appear at the Journal of the Royal Statistical Society, Series A. Okay. Okay, there is a huge literature studying family size, citizenship, and their consequence in economics and psychology. For example, in economics, Baker and Lewis wrote a famous paper proposing this notion, quantity and quality interaction. And basically, they pointed out there's a trade-off between the number of kids and the quality of them. And after Baker and Lewis, there are several empirical research papers finding negative association between the family size and school achievement. But after those early papers, people also found non-negative associations based on probably different population and different measurements of the outcome. And recently, there's a paper by Mark Stadt and Wilswall pointing out there must be a complex and heterogeneous effect, or actually nonlinear effect of the number of children on economic consequences and psychological measures. And psychologists have slightly different views because they think sibling companion will affect psychological health positively. So you can see there's a different view from economics and psychology. It's a little unclear whether increasing the family size will increase the quality of kids or decrease. And it's also of interest to see whether the Chinese population have a similar pattern or different pattern. And there is a natural experiment for us due to the one-child policy during 1979 to 2015. For those who were not born in China, let me quickly introduce this one-child policy. Everyone knows there is a one-child policy. Every family can only have at most one child. And the policy was imposed in 1979. It's a little complicated because at the beginning, there are a lot of variabilities going on. It's not very restrictive at the beginning, but in different provinces and the implementation intensities are different and so on. And after a while, the policy stabilized. And in 2015, the government ended the policy. So now every Chinese family can have more than one child or two children. Okay, and there are already a lot of discussion about being an only child in China and its consequence on well-being. For example, there was a science paper by Cameron et al. They found a negative effect of being an only child on psychological health, and they call the generation of little emperors. And they leveraged a natural experiment on individuals born just before and after the implementation of the one-child policy, OCP from now on. Okay, and they think maybe individuals born just before and after the policy implementation, there's no systematic difference. So it's like a pseudo randomization generates a binary instrumental variable, and they use this pseudo randomized experiment to estimate the causal effect of being the one-child policy. Okay, and overall they found being an only child in your family will make those kids less trustworthy, more pessimistic, and risk-taking. So negative result. But this year, well, there's a recent paper from some Chinese economists. They found positive effects of being one child on life cycle outcomes, because another dimension is because someone is the only child, he or she has all the resources from the family, and he or she will have better education resources. So they found positive outcomes on education income. Okay, so you can see there's no coherent conclusions. And we use this China family panel studies as our data. So this is a publicly available data set hosted by Peking University. You can download the data. And this China family panel study, CFPS, was launched in 2010 by the Institute of Social Science Survey, and it's nationally representative annual longitudinal survey of Chinese communities, families, and individuals. And it also contains a lot of variables measuring economic and non-economic well-being of the Chinese population. And we analyzed the data from the first national wave in 2010. It is a subset of this big data set. The subsample consists of children born after 1979. So in our subset of data, those units have age ranging from 16 to 31. Here is some summary statistic of family background of those units, those 3 columns, all samples, an only child, and those children with siblings. And the variables are maternal education, paternal education. And you can see there are some differences in the years of education of mother and father, and only children have mother and father with more years of education. And these two are the maternal and the paternal age and birth, and not much difference here. And family annual income measured in 2010 by Chinese yuan, and you can see only children were born in like richer families. So you can see the difference. There is a small difference in the divorce rate in the families of only children and family with multiple children, and slightly higher divorce rate. And the second table of summary statistics are the individual information, like the age of the children. You can see the only children are slightly younger. This is by construction, because if someone has siblings, we only use those units from who are the oldest. Okay, so we don't use younger children from a family. By construction, only children are younger in our data set. And number of siblings ranges from 2 to, family size from 2 to 4. So number of siblings from 1 to 3. You can see that there's the difference here. And there's the background information. Most Chinese people are Han ethnicity. But the only child policy was only imposed on Han people. So if you are from families of other ethnicities, there's no restrictions on the number of children. So that's a background information. So you can see this variable, the binary indicator for Han ethnicity. Only children are from, more of them are from Han family, and small proportion of children with siblings are from other ethnicity. So the proportion of Han ethnicity is smaller here. And the last table of summary statistics are the 3 outcomes we will analyze: confidence measure, anxiety measure, and desperation measure, ranging from 1 to 5 is ordinal data. From this marginal comparison, there's not much information going on, because only child and children with siblings have very similar outcome measures. But this is not a very meaningful causal comparison because we ignore all the important background covariate information. So our later analysis will conditioning on those important variables we reviewed. But nevertheless, we can see children with siblings here have slightly higher outcome measures. It's very small, but at least is positive difference. Okay, so these are the main variables we select from this database. It's a little challenging to do statistical causal inference with this type of observational study because being an only child or not is not randomly assigned. There is confounding between fertility choice and psychological health. There are some measures confounding we already collected. For example, children's age, number of siblings, and maternal, paternal education, age, and income. So these are the measured variables. We believe they are very important, but there are other important variables unmeasured. For example, the nurturing environment of a family. It's hard to quantify that variable, and we believe there are some important hidden things going on affecting both fertility choice and psychological health. And how do we deal with unmeasured confounding in observational study? Usually we need to find a more exogenous shock that affects the fertility choice only, not affecting the psychological health directly. Okay, and that shock must be kind of randomized, or at least more randomly assigned than being an only child or not. And previously, several economists leveraged the randomly assigned intensity of the one-child policy, because as I mentioned at the beginning, even though there is a national policy, when it is implemented, it's not uniformly implemented in different places, the intensity were quite different. There are some previous papers use fine rates as a proxy variable to this implementation intensity. And Anthony created an indicator called IFPPR, indicator of family planning policy resistance. Basically, it is another measure of a fine rate or how rigorous this OCP is in that province. So this index is province level index. And Wu previously used this index as instrument variable to analyze a subsample of this CFPS. And he used some standard econometric approaches. I will review his approach a little later. Okay, this is a map of China. And this map shows the IFPPR distribution, which varies across provinces. There are some with darker sides indicating high level intensity. You can see provinces in the coastal regions have higher intensities, but sometimes like in Inner Mongolia and in Sichuan province, where I'm from, have also very high implementation intensity. Okay, so this is some rough idea about this variability across provinces. And Wu's IV analysis used two-stage or three-stage least squares, assuming constant effect. And the problem of this data or this problem is the IV varies only across provinces. There's not much variability there. It's constant within province. So we have a clustered IV because units from the same province will have the same value of IV. It's a very classical clustered data problem. And the outcome is complicated in the sense of being ordinal. It's not like a linear model. So we take a slightly different approach. It's still instrumental variable analysis, but it's more sophisticated IV model proposed by Hickman. It's called the local instrumental variable framework. And we combine it with Bayesian hierarchical models because we have clustered data. And we also assess the sensitivity of the results with respect to possible violations of the exclusion restriction. The key assumption required by the instrument variable analysis. So these are the two main points. And let me introduce the formal statistical framework. There are n units from a population of units. And in our analysis, we define 4 subpopulations. Basically, we analyze 4 subgroups independently. So the 4 subpopulations are defined by male and female and urban and rural area, because a priori, we believe these two binary variables are very important with respect to both the treatment, being an only child or not, and the outcome of psychological health. Because male and females are quite different, or they're treated differently in China, and the urban and rural areas of China are also quite different. So we believe these 4 subpopulations are meaningful subpopulation a priori. And each unit belongs to a cluster, CI, representing the province of birth. And we use XI to denote all the pre-treatment covariates, including demographic and family background, all the covariates that I reviewed before. And TI is the binary treatment indicator, with 1 being an only child and 0 otherwise. And outcomes, we have 3 outcomes. So we analyze 3 outcomes independently. 3 self-reported measures of psychological health that I showed you before, confidence, anxiety, and desperation measures. And the instrument variable is continuous. And for convenience, we take the negative value of the IFPPR created by Anthony. It's a bounded instrument variable. The reason why we take the negative value is for easy interpretation. With larger instrument variable value, there's a higher probability of being an only child. Okay, that's for descriptive convenience. Here are some formal notation to quantify causal effect. And we define TIZ. Z is the instrument variable. This is the potential treatment, hence the IV of the unit I taking the value little z. And the YIZT is the potential outcome of unit I if he or she is exposed to IV value Z and treatment T. And our observed treatment is TI and YI. So TI is a function of the potential outcome and the IV value, and the observed outcome is the function of the potential outcome and the observed value of the IV and the treatment. Okay. Of course, there are some hidden assumptions. For example, we assume there's no interference among units. And the first important assumption is the IV is exogenous given observed covariates. Conditionally on background covariates X, the IV value is independent of all the potential outcomes. It's a kind of reasonable assumption if we have enough background covariates, if we believe the intensity of the implementation is randomly assigned. But maybe you don't believe this. You think different provinces may be different. There are some hidden reasons for the different intensity. So in that case, this assumption 1 will be violated. But this is our assumption. At least we believe the intensity is more random than the treatment itself. And the IV is now weak, meaning it's a real IV. The intensity of the policy will affect the probability of being an only child. Okay, these are the 4 plots based on some statistical models we fit later. Okay, 4 curves for rural females, rural males, urban females, urban males. So the x-axis is the quantile of the IFPPR, the intensity of the IV of the policy, and the y-axis is the probability of being an only child. You can see for rural females, the probability is much smaller. Why? Because in rural areas of China, people held the traditional thinking that they really want males for their family. That's why if they have had a girl, they'll try to even break the law to have another male, another boy, I guess. That's a very common thing in rural areas. That's why the probability is quite small. For males in the rural area, the probability is significantly higher. And in urban areas, you can see the difference becomes much smaller. So, still, lower probability of being an only child for females in urban area, but the gap is much smaller. And overall, there's a huge gap in urban area and rural areas. This is quite reasonable based on our understanding of the society and family structure in China. And you can see there is very significant or very obvious pattern. Its probability is non-degenerate and it's increasing in the IV intensity. And it's a real IV, or it's now a weak IV. Some further assumption. So this pattern is the monotonicity on average. So if we increase the probability will increase, but we need stronger assumption for IV analysis. This says the treatment indicator for every individual eye is increasing in IV intensity. This is the potential outcome, increasing in Z. This extends the monotonicity on binary IV. So there's an Angrist-Imbens Rubin paper on binary IV. Here is a continuous IV. It's an assumption on individual behavioral type. We cannot really verify this assumption. But at least the data do not provide contradiction to this assumption. We observe monotonicity on average. We need this individual assumption. Assumption 4 is the key assumption for instrumental variable. It's called the exclusion restriction. It says the intensity of the IV affects the outcome only through the treatment indicator. Or in the end, this potential outcome indexed by IV and the treatment only depends on the treatment indicator T, which is binary. Okay. There's no direct effect of this instrumental variable on outcome. But maybe the intensity will affect the outcome through other causal pathways. For example, if some province have very high intensity of this OCP, people may move to other places. Or some families even divorced and because they want another child. If someone is divorced and he or she remarries, then he or she can have another child. That's allowed. That's why it's possible this IV can have other pathways. But from our investigation of this data, the proportion of divorce, as I showed before, was quite low during that time period in China. It's much higher now, but at that time, it was low. And the migration rate was also pretty low in this subsample. So we will simplify, as a starting point, we believe this exclusion restriction, but later we will conduct a sensitivity analysis. If we believe this exclusion restriction, we can write the potential outcome as a function of only T, not Z. Okay. Generally, these assumptions are not directly testable based on observed data. We must make some untestable assumptions in causal inference. Here are some parameters of interest. Based on potential outcomes, we can define causal effects clearly. The first one is the standard average causal effect on the treated. So for those single only child, what is the effect of being the only child in a family? And the second one is the policy relevant treatment effect proposed by Heckman. So it's slightly different. It's a subgroup causal effect, still comparing Y1 and Y0, being an only child or not, the average, but only for a subpopulation changed by the policy. So this means at the lowest intensity, the children will not be a single child. But at the highest intensity of this policy, this child will be a single child. Okay, so this child or the family of this child, the families that are changed by the OCP, the fertility decisions were changed from 0 to 1 by this policy. That's why it's called policy relevant treatment effect. The final one is a little complicated effect called marginal treatment effect. It will have a simpler form later, but at this point, I give you the original definition. The original definition is the average causal effect for those family or for those children. At intensity Z, he will be an only child. But at a lower intensity, he or she will not be a single child. So he or she is at the margin of this policy. So just changed by the policy right at the intensity Z. That's why it's called the marginal treatment effect. Okay. I will use other notation to hopefully simplify the interpretation of those estimates, 3 estimates. The policy relevant treatment effect and the marginal treatment effects are local effects. Local means subgroup. Okay, local effects defined by the joint potential values of T, defined by the collection of TIZs for all values of this intensity of the IV. This is a huge vector. And Frangakis and Rubin call this principal stratification. And we can simplify the representation of the problem using some selection model framework due to this econometrician. And he showed under those assumptions like monotonicity and so on, we can write TIZ as indicator of VZ larger than or equal to SI. Let me explain the meaning of this. So this is a representation. So this is what we, hopefully we can observe given the potential outcome, given the intensity of the IV, this is the potential outcome. But the right-hand side is representation using other latent variables. For example, this SI is the latent threshold measuring the utility of violating the OCP. And VZ is a function of Z. And for simplicity, we can just take VZ as Z, because otherwise we can just apply the monotone transformation V inverse on both sides. It does not change the inequality. So for simplicity, you can read this as Z. Okay, Z is the intensity and S is the utility. If the utility is lower than the intensity, then the family will have only child. Because the utility is too small, they will not decide to have more children. Okay, that's an interpretation of this principal stratification or interpretation of this selection model. And for simplicity, from now on, we will call SZ the principal stratification because almost SZ determines TIZ. SZ determines the left-hand side, but the reverse is not correct. The TIZ may not completely determine SZ, but because our model will involve SZ, we call SZ principal stratification. Okay. So with this new selection model representation, we can rewrite those estimates in this form. First, the marginal treatment effect can be written as the average treatment effect for this latent population indexed by little s. So the utility takes value s. It's much simpler than this formulation. Okay, so this formulation is those units at the margin of changing their behavior at the intensity z, which is the same as SZ taken value, SI taken value z, because those units at the margin. If you change the variable z a little bit, the indicator will change from 0 to 1. Okay, this is the marginal treatment effect. And we can rewrite ATT as the average of marginal treatment effect over the distribution of Z for those treated units. And the policy relevant treatment effect as the average of those marginal effects over the latent strata within the range of the policy of this IV. Okay. And in some sense, we can write all the interesting causal effects in terms of marginal treatment effects. The marginal treatment effects are the building blocks for everything. And we will actually focus on this marginal treatment effect because it gives us more interesting patterns of the causal effects. Given the utility interpretation of S, it is the utility of violating the OCP. Okay, how do we estimate those causal effects? So we rely on some Bayesian models. Because the data structure is quite complicated. Using standard method, it's not very convenient. So we use a more coherent and sophisticated Bayesian modeling. So these are the variables we have. Instrumental variable covariates, potential outcomes under treatment and control, and the principal stratification variable SI. So we factorize 5 variables into 3 parts: distribution of X and Z, distribution of the principal strata given covariates, because Z is randomly assigned, so it's independent of S. We drop Z here. Same thing, we drop Z in the first factorization. This is the distribution of the potential outcomes given principal strata and covariates. We don't want to model the last piece because these are the background information, covariates and IV. And the second piece is called the selection model. It's the decision of the binary indicator of a single child or not. Equivalently, it's the model for the latent utility. And the first piece is the distribution of the potential outcome. That's a key component because it quantifies causal effects. So we will focus on 1 and 2. First, how to model the latent utility. We model it in this way. Latent variable is a normal random variable, some function of covariates and some random effects. And this T, binary indicator of one child, single child or not, is whether this utility is smaller than or equal to the intensity of the policy. If it's smaller, it's single child, otherwise with siblings. Okay, this R is the random effect for the principal stratification. Second is the outcome model. We model it as a proportional odds model because Y is ordinal from 1 to 5. So this is a proportional odds model. Under the logit transformation, the CDF, the distribution function is a linear form with different intercepts corresponding to the category K and this random effect for province effect. Okay, so both models are kind of standard because this is a binary selection model. We just use, this is kind of random effect probit model. This is random effect proportional odds model. Both are standard. And we impose conventional priors for those coefficients and random effects. There's some details in the paper. I don't want to talk about those things because we use pretty standard priors for Bayesian computation. And imposing those priors allows us to simulate the posteriors of all those parameters. If we can simulate the posteriors of those parameters, the causal effects we defined before are just functions of those parameters. Okay, I omit the details of the calculation, but you can do the calculation once you simulate the posterior of the parameters. You can simulate the posteriors of those causal quantities of interest. So this is the most important figure in my talk. It's quite complicated. Let me explain. It's 3 by 4. 3 rows corresponds to outcomes, confidence, anxiety, and desperation measures. 4 columns correspond to 4 subgroups: rural female, rural male, urban female, and urban males. 4 columns. So the x-axis for each subfigure is the quantile of principal strata. So this S variable here, the utility of violating the OCP, it's continuous. So we transform it to be between 0 and 1 by its quantile. And this y-axis is the marginal treatment effect, the MTE, as a function of S, as a function of the quantile. Okay, you can see almost for all the subfigures, except this one, there's a decreasing trend. I will interpret this decreasing trend later, but the pattern seems coherent. And for rural male, there's no effect at all because it's close to zero, and the credible interval, the 95 credible intervals cover zero. There is some negative effect for rural females, especially for confidence measure. And there is much more significant patterns for urban population, either urban female and male. For males, seems effects are more negative. And for females, the effect is comparable, slightly smaller, especially for this confidence measure. Okay, so you can already observe the heterogeneity in rural area and urban area. So since those urban kids were hurt more in terms of psychological health by this policy, and the rural kids were better because maybe they have other companions of kids from other families. I will give you more interpretation later, but this is the figure we can immediately compute from the spacing modeling. Okay, so maybe the next slide contains more interpretations. So the 4 subpopulations have different patterns. There's no significant effect for rural males, and a small negative but significant effect on confidence for rural females. And this is a repetition of what I said. There are negative effects for urban subpopulations for all measures. And only children might subject to more pressure from parents, which influence psychological health. That's our conjecture of this negative effects. And rural children may have less restrictions to communications with peers. So like these 2 columns, the effects are no effect and the effects are smaller. And our conjecture is they can easily communicate with peers from other families, leading to less harm due to this policy. Maybe urban kids didn't have this luxury. And another interesting we found, these are the heterogeneity with respect to observed variables, urban or rural area, and male and female. There is an interesting thing that's very unique, unique to this local instrument variable framework is the heterogeneity with respect to a latent variable, the latent utility. You can see the decreasing trend says if the families are more resistant to the policy, the effects are more negative. So the decreasing trend. The interpretation is the families may be less prepared to educate their children if they prefer more children. That's our conjecture from this decreasing pattern. But overall the effects were quite small. The patterns are coherent across many measures. Okay, there are some other analysis I will quickly go through because I only have 10 minutes. So these are the aggregated estimates. That's the marginal effects. This is the average treatment effect on the treated and the policy relevant treatment effect. The average over all principal strata for 3 measures. And you can see a similar pattern. For urban female and male, the effects are more negative. And for other population, there's no significant effects. And the ATT and PRTE are quite similar. Although theoretically, the averaging over different populations, but we have some diagnostics showing in this data set, the average, the treated population and the policy relevant treatment effect population have huge overlap. That's why they do not differ that much. So there's some heuristics confirming my claim. So this x-axis is the value of the principal strata. Y-axis is the probability. So these are the distribution of these 4 subgroups. And these 2 lines are the range of the intensity of the instrument variable. So most units are within this region. So these units will be changed by the policy, because most of them are in this region and most of them will become treated population. So these 2 estimates have very similar latent populations, giving very similar estimates here. Okay. Here is a comparison with other methods. The comparison is not a fair comparison, because the most interesting thing for our analysis is the decreasing trend with respect to the latent utility. And this comparison is based on the aggregated estimate. And those estimates are not necessarily comparable. For example, the least squares estimates are estimating the whole population. The 2-stage least square is estimating the compliers. And the Bayesian local IV are estimating something different. They are the same under the constant effect assumption, but they differ in general. And you can see they actually differ a lot. For example, here our estimates is negative and significant here, negative and significant here, but for 2-stage least square and OLS, they're not significant at all. This is a little unusual, because usually we have very significant least square estimates, but there's no significant results from instrument variable analysis. But from this particular data set, this is not true. And we believe this is not the most interesting figure. The most interesting figure is the marginal treatment effect curves showing the pattern. Okay, the final slide of analysis is my promise at the beginning. If you do not believe exclusion restriction, what can you do? You have to do some sensitivity analysis showing how sensitive is your result with respect to the violation. But we have to parameterize the violation. There are many possible violations. How do we talk about the violation? So here is a simple quantification of the violation. We use a single parameter R to quantify the proportion of direct effect of the instrument variable among the total effect. So remember, what does exclusion restriction mean? It means all the effect of the instrument variable are through the treatment itself. There's no direct effect of this instrument variable on the outcome. So the violation can be quantified by the proportion of the direct effect. Okay. Here's a simple illustration of the point estimate of the average treatment effect on the treated and the PRTE. It's depending on your view of the problem, it can be claimed to be not that significant, because unless you believe the proportion of the direct effect is larger than 10%, your conclusion will not be changed. Okay, but if you believe 10% is a small number, then the conclusion can be sensitive. Okay, so roughly speaking, 10% is the critical value to overturn the conclusion. And we didn't do the sensitivity analysis for MTE curves, partially because it's not that easy to show the curves with respect to another parameter R. So that's a very simple sensitivity analysis. Okay, let me summarize. In our analysis, it's a very elementary analysis. We view it as exploratory data analysis. Maybe compared to other economic or sociology empirical research, this is a very simple analysis. So we use OCP implementation intensity as an instrument variable in a natural experiment based on the China family panel study collected by Peking University. And we found that being an only child harms self-reported psychological health measures. So you can criticize the analysis from another dimension because it's self-reported. There is maybe huge measurement error in those measures. The interesting findings are treatment effect heterogeneities with respect to observed variables, rural, urban, male, female indicators. And more interestingly, the unobserved latent tendency to obey the OCP or the latent utility. The more resistance, the more harmful. That's our basic conclusion. And Hickman's local instrumental variable framework is central to analysis because other framework cannot reveal the latent heterogeneity with respect to the utility. And we believe Bayesian method is more appropriate for this type of data analysis, which can accommodate several data complexities. For example, the clustering data structure and the more complicated ordinal data structure. Linear model is not the best model in this case. Okay, so that's my conclusion for this talk. I still have 3 minutes for questions.